In our previous lessons, we have learned various principles which are important for counting. These principles are multiplication principle, addition principle, counterpositive or the contradiction principles, right? We have also learned the arrangement and subsets and how the multiplication principle is used to do the arrangement and how to find those subsets using those multiplication principles. So there is one more important principle which is very crucial, and this is used in solving the various problem in the counting. So let's talk about this principle which is called a bijection principle. Let's take an example. So there are 5 car parkings, right? So there is, we say this is car 1, car 4, car 5, car 3 and car 2, right? So we say that the parking lot is full when all 5 parking is taken and each car is parked in a parking space among the 5 parking space, right? So if we know that and we say that the car parking is full, then we can clearly say that there are only 5 cars because there is only 5 parking space, right? So this is one of the basic example of the bijection principle. Before learning the bijection principle, we have to learn a little bit of function. If you are not aware about it, I'll go here, right? So function is nothing but mapping of f. So we call the f as a mapping from a set A to set B, right? This function is called 1 1 or 1 to 1, 1 to 1 when. So let's say this set has all the elements as so it's called 1 to 1 if for all elements in A. So let's call this A as an element. For all elements in A, so A belongs to A for all, right? There exists element B in the set B, whereas FA is equal to B, right? So you can see that we are using this language of mathematics. So for all A belonging to A, there exists a B such that FA is equal to B. So meaning by for all elements in A, there should be a unique element in B, and this needs to be unique. This needs to be unique. There exists a unique element, you can say unique element. So if this element is A, is this element B is unique for all A, meaning by Fx can't be equal to Fy, where meaning by, so there can't be 2 elements in A which will map to the same element in B, right? So this is called 1 to 1 function, and we also call it injective function. Okay, so this is, we call it as injective function. So there is another thing that there is another type of function which we call as onto function, onto or subjective. Okay, subjective function. So it says for all elements in B, for all elements B belongings to set B, there always exists element A in A where FA is equal to B. So there always exists element A in A belongs to A. So if this condition holds, then it is called onto function. So let's take some of the example of the function to get the clarity of injective and surjective or 1 1 or onto, right? So let's take example. This is a set A and this is a set B. And we define the mapping F in this one. So this set has, let's say, element -2, -1, 1 and 2. And here we have elements like 3, 4 and 6. Okay. Now let's define the mapping as this, that 2 is mapping to 3, -1 is mapping to 3, 1 is mapping to 4 and 2 is mapping to 6. Okay, let's take another example. So we take the another set, let's say C, and this is B. Okay, so here we have elements, let's say 2, 3, 5, and here we have elements 1, 6, 8, 9. So 2 is mapped to, let's say, 6, 1, 3 is mapped to 8 and 5 is mapped to 9. Okay, now let's take another example. So we have another set. So this is, let's say, first function. This is the second mapping. When we have third one is, let's say, R set, and this is S set, and the mapping, the third mapping is defined with the elements here is 2, 4, 6, and here we have elements like 1, 2, 5, 7. So 2 is mapped to 1, 4 is mapped to 1 and 6 is mapped to 5, let's say. And finally we take the fourth example, fourth set, fourth mapping, as you can see here. So I'll take the fourth mapping here. So this is the third one, this is the fourth mapping finally. Again, let's say it is B and this is C. Well, it doesn't matter. So it has elements 1, 2, 3, and here we have elements 4, 5, 6. 1 is mapped to 4, 2 is mapped to 5, and 3 is mapped to 6. Okay. Now, so we draw a table here to see which functions are injective or one-to-one and which functions are onto or surjective. So we draw a table here, right? So we write the function numbers here. So this is our function number 1, 2, 3 and 4. So this is our function 1, 2, 3 and 4. This is one-to-one and this is onto. So this is injective and surjective, right? Oh, sorry, we have to give them some space. So this is function number, right? Function number, functions or mapping, and this is one-to-one and this is onto, right? So if you look at the first function, the two numbers from A map to the single number B. So this cannot be injective or one-to-one because each member should have a unique, mapping in B, right? So this is called domain and this is called range also. But we will not go deep into it because when we go to the function and its analysis series, we will deep dive more into it. So this can't be injective. But all the three numbers here in B has some element in A, right? So this is onto. So we have to, yeah, this is onto. We took at the second example. Each number is, each number in A has a unique number in B. In C has a unique number in D. So this is injective. But if you look at it, there is an element 6 in D which is not mapped to any element in C, right? So this can't be onto. So this is not onto, right? Let's look at, let's take an example of 3. So here we can see that 2 and 4 are actually mapped to 1. So this can't be injective or one-to-one, right? And there is a number 2 which is not mapped to any number in A. So this can't be onto as well. But if you look at the fourth one, there all the numbers in B are mapped to unique number in C, and similarly all the numbers in C have a number in B, right? So this is 1 1 and this is onto. Now let's try to see what does this bijection principle say, right? So the bijection principle is says, so we write it as the bijection principle, right? Bijection principle. C. Okay. So what does this bijection principle say? So it says that mapping from A to B is a mapping. If it is 1 1 1 to 1 and on to, then cardinality of A is equivalent to cardinality of B. Meaning by the number of elements in set A should be equal to number of elements in B, right? So this is a very crucial and one of the mostly used principle in counting. So what happens is that there are certain kind of problems, right, where the counting looks really difficult. And if you can draw parallels of one-to-one relation and on-to relation with a certain different problem where you can easily count, then you will be able to count the first problem. So I'll give you a few of the examples which will help you to understand more of this bijection principle here. So let's take an advantage of the bijection principle and let's see how this can be done easily, right? So let's take the first. Okay, so we have already taken one example earlier. So we'll go back to that example and see how we can find that, right? So the problem statement, problem number 1 suggests there is a circle, right? So it's not a circle, but yeah, okay, you can say that there is a circle. Okay, so there is a circle, okay, and it has 5 distinct points as 1, 2, 3, 4, and 5. Okay, now if you want to find the number of chords, right, in this circle, the chords are nothing but joining these 2 points, 1 5, 1 2, 1 3, 1 4, and all this stuff. So how many chords can be formed with 5 distinct points on a circle, right? So this is the question. Now let's try to do a parallel of one-to-one function which can be formed using this. So if you look at it, so let's say we have a set A which has elements 1, 2, 3, 4, and 5, right? Now we want to find the subsets of A with 2 elements. Okay, and this is B of all the chords, right? So let's try to draw a parallel between let's try to find a one-to-one and on-to function between these two sets A and B. Okay, so any chord can be found like with joining these 2 points, so that this could be 1 5, this could be 1 2, this could be 1 3, and 1 4, right? So you can write it like 1 5, this is 1 4, so this is 1 3, this is 1 2, and so these are the various chords you can form, right? Now if we write all the subsets of this, then these subsets could be again 1 2, 1 3, 1 4, and let's say 1 5. So these are the various subsets which we can form from 1 to 3 4 5. So if you take a close look at these two things, that each and every chord which is 1 5 will be present here, and so forth. Every subset of A will be the number will be there in the chord, right? So we draw a parallel that these two A and B are bijection to each other, right? So we can easily see that I leave up to you to find that A and B mapping is a bijection. Hence it is we can always find the number of subsets of A, and similarly that will be equal to the number of chords in B, right? So how many subsets of A can be found with 5 digits? And we have seen that earlier that this is nothing but, you know, uh, finding the combination out of finding the two combination, finding the combination of two objects from 5 objects. That is nothing but 5C2, which is nothing again but 5 into 4 divided by 2 into 1, which is 15. So there will be 15 chords which can be formed from a circle with 5 distinct points. So these two are, once the bijection is set, you can simply count the easier part, because this is the easiest. This is an easy to count because it's simply the combination, finding the two element combination from 5 element set, and we have done that earlier as well. So this is one of the example of the bijection. Let's try to look at one of the more difficult kind of a problem, right? So I have this problem with me. Okay, so let's try to solve this problem. This is the problem. Let's draw a 2 4 rectangular grid with two specified corner P and Q. So I'll just draw that for you. Okay, so this is 2 by 4 rectangular grid. This is 1 2 3 4, and this is 2. Right, this is 2 by 4 rectangular grid. 1 2 3. Okay, right. So this is 2 by 4 rectangular grid, and the point P is denoted here as P, and this point is Q, right? So there, you can see that there are 12 horizontal lines. So 1 2 3 4 5 6 7 8 9 10 11 12. So there are 12 horizontal lines and 10 vertical lines. So 1 2 3 4 5 6 7 8 9 10, right? So in the grid, right, a shortest path PQ is a route continuous path from P to Q consisting of 4 horizontal segments and 2 vertical segments. So let's try to draw such short path, right? So we have to have 4 horizontal segments. So we can go from here, then we move here. So we draw it like this. So just right. Then we move one vertical. So we have one vertical, and again we have 2 horizontal here, 2 horizontal here. So there are 4 horizontal segments and 2 vertical segments. So this could be one of the shortest path between P and Q. So how many such shortest PQ routes are there in this grid? Right. Now you can simply try to count this. Like for example, you go here, then another shortest path could be this. But if I increase the number of grids, it will be really difficult for you to count, right? But let's try to find bijection between two sets. So let's say this set is A, which is all shortest path, which is defining, we have defined it like that, shortest path from P to Q. P to Q. And then we have a set B, which is nothing but a binary sequence, okay, of 6-digit numbers, 6-digit number, where we define the horizontal parts as 0 and vertical parts as 1. So this binary sequence will be 2 zeros. Then we move the horizontal part, the vertical part, so that is 1. Then we move 2 horizontal again, so again 2 0. And then we have moved one horizontal part, vertical part, right? So this binary sequence is this. So this set is set of all such binary sequence. All such binary sequence, right? Now, if we look at this one, so we move 2 verticals, so 1 1, then we move 4 horizontal. So if you pay close attention, that set A and B, there is a bijection between set and B, where the set B could be defined as, set B is defined as all binary sequence which has exactly two ones in a sequence of six, in a where the length of the binary sequence, of sequence is 6. So the B is a state where, so if you look at, let's try to draw another one. Let's see. So we move here 1, right? So that binary sequence will be 0. Then we move 1 here, right? So that will be 1. Now we move 3 steps here. So we'll have 3, 0, and then we move 1 again here, 1. So we draw a parallel and find different set. So we define this set B is defined as all binary sequence which has exactly 2, which has a length of the sequence is 6, and we know how to solve this problem, right? So we have to find two ones out of this 6 binary sequence, which can be done via 6C2. So finding the two combinations of 1 among the 6 places, right? So this can be done via 6C2, which is again nothing but this, again 15, right? So we are able to solve this problem, quite easily here using the bijection principle. We found a bijection between a set A and B, and then we have counted all the all the elements in A, B, and hence we deduce that all the elements in A are same. So the number of count of shortest path from P to Q with this condition is same as the finding the all binary sequence of length 6, which has exactly 2 ones, right? So this is one of the another example. Let's try to look at the slightly more complicated example. Okay, so for that to happen, first we have to understand one very important number theory concept. So we say so let's say when we say A divides B, it says that when B divided by A, the remainder here is 0, right? When we say A divides B, the remainder should be 0. So for example, 9 is divided by 3 is true. Similarly, 10 divided by 2 is also true, but 9 cannot be divided by 2 because the remainder here is 1. So this is false, right? So now let's try to so there is another basic number theory thing. So for that to understand, you have to know all the primes. So prime factorization is one of the very crucial number theory concept. If you are not aware about the primes, let me tell you. So the prime numbers are 1, which can be divided by 1, and that number itself, it cannot be divided by any other number. So the example of primes are 1, 2, 3, 5, 7, and henceforth. You can write 11, 13, and henceforth. So it says any number n, prime factorization law says any number n can be written as product of power of primes, P, Q, R, let's say S, right? So it should be P2 into R2 and PQ into R to the power S. So let's take an example. So we have, okay, so let's say 72, for example. So 72 can be written as 8 into 9, which is 2 to the power 3 into 3 to the power 2, right? So you will always find P1, P2, PQ primes with certain powers that will define any number. So you can try this, and because this is a very fun exercise, so any number in this number line can be written as a product of power of prime. So this is a very important prime factorization rule, right? So now let's try to see how we are going to, okay, so let's try to find all the factors of 72. Right now, when we say factor, all the numbers which will divide 72. Since 72 is a very small number, right? So you can try that, okay, 1 will be one factor, 72 will be another factor, 2 will be another factor, 3 will be another factor. And you can count all those factors. But let's say this number is big. How we are going to find the primes? How we are going to find the number of divisors of 72 or factors of 72? Now this is looks, so let's say we take a big number, right? So we have another big number. Let's say we have, yeah. So let's see this problem. Okay. So the next problem which we are going to attempt is this: find the number of divisors of, let's say, 12,600. Now, I'm not sure that you will be able to find all those numbers, all the devices by writing all these devices. With 72 you can try that, but we need to find a principle or method so we can find all these things. So let's try to see how we can find all the factors of 72, right? So we write this as, okay, 72, and we have 2 to the power 3, right? This number is 2 to the power 3 into 3 to the power 2, right? Okay, now let's try to see how we can do that. So we'll try to write all those all those factors which are different. So first one will be 2 to the power 0 into 3 to the power 0, right? The second will be 2 to the power 1 into 3 to the power 0. The third one will be 2 to the power 2 into 3 to the power 0. And finally, there will be 2 to the power 3 into 3 to the power 0. Similarly, we can write 2 to the power 0 into 3 to the power 1, 2 to the power 1 into 3 to the power 1, 2 to the power 2 into 3 to the power 1, and 2 to the power 3 into 3 to the power 1. So if you look at it, that all these numbers will divide 72. There is another possibility. We can write it 2 to the power 0 into 3 to the power 2, and 2 to the power 0 into 3 to the power 1, 2 to the power, sorry, 3 to the power 2. 2 to the power 2 into 3 to the power 2, and 2 to the power 3 into 3 to the power 2. So we can, if we can count this, then it will come down to 12 such numbers, right? So there will be 12 divisors or factors of 72, 12 factors, right? But if we have to write this for, a bigger number, so 12,600, it will be really difficult for you to count like this. So what is the bijection which we can draw from here, right? So if you remember in the basic set theory, we have used certain thing called Cartesian product, right? And we have shown that the Cartesian product is nothing but the multiplication principle, right? So what is the Cartesian product? What is the two Cartesian sets? So we define the set C here as A Cartesian B, where A is between 0 to 3 and B is between 0 to 2. So this is nothing but the Cartesian product of A, which is 0, 1, 2, 3, and B, which is 0, 1, and 2, right? And by the multiplication principle, we simply know that this Cartesian product, the cardinality of C is nothing but cardinality of A into cardinality of B, which is nothing but 4 into 3, which is again 12, right? Okay, so which is again 12. So this is the use of the Cartesian product mapping, right? So now how do I reach that? How do I define this bijection as the Cartesian product? So what here we are trying to do, if you look at closely, what we are trying to do here is we are saying we are trying to find these two numbers. Let it be P and Q, right? P and Q. So this is what we are trying to do is P and Q doublets such that first is from this state and the second is from this state, right? So this is 0, 1, 2, 3 and this is 0, 1, 2, right? So we are finding all these couples and then we are simply using the Cartesian product. So this rule can be generalized and we can form the various, so we can now try to solve this problem, right? Find the number of divisors of 12,016, okay? So we'll move this problem here now. Okay, so we just copy it. So we'll try to copy this and paste it here. Okay. Okay, so let's try to find all divisors of 12,600. 12,600? 12,600, right? 12,600. 12,600. So this is nothing but, let's see, 8 into 9 into 25 into 7. Okay, so 8 into 25 will give you what? 8 into 25 will be 200. 200 into 9 is 1800, and 1800 into 7 is 12600. So this is again nothing but 2 to the power 3 into 3 to the power 2 into 5 to the power 2 and 7 to the power 1, right? So if you look closely here, what we have done is that we have included 0. So what we have done here is by multiplication rule we have included 0 here as well. So this set will have 4 elements, this set will have 3 elements. So similarly in this case, the first set, it will be a Cartesian product of 4 sets. So the first set will have cardinality of first set will be 4, right? This will have cardinality 3, this will have cardinality 3, and this will have cardinality 2. So the total number of divisors will be 4 into 3, which is 12, into 6, 36, and 2, 72. So there will be 72 numbers which will exactly divide 12,600, right? So this is one of the few examples of the bijection principle, and this shows you how powerful is the bijection principle. If you are able to draw another set which is quite similar to what you are looking for, and if you can count that one easily, then you will be able to count the other part easily. So that is one of the key role which the bijection principle see. We will see the use of the bijection principle in the various distribution problems which we are going to take in the next session. For this section, so we conclude this session here. Thank you.